Hello everyone, welcome to the series of lectures on applications applica- of linear algebra. So mostly to cancer biology. So this is a kind of a personal and scientific mission. This is dedicated to my brother who fought bravely but was failed by the blunt instruments of current treatments of cancer. So cancer took his life, but it was the treatment, the brutal equilibrium between killing tumors and sparing organs. It was supposed to save his leg and his life, but ultimately it proved lethal. This series emerges from that loss with a conviction that mathematics can make cancer therapy more precise and less cruel. So, what is linear algebra and why? So, because tumors are not just biological entities, they are mathematical systems where every metastasis is a vector. Every metastasis is a vector in a high dimensional space. And every drug interactions form matrix equations. And the treatment resistance emerges from eigenvalue dynamics. Okay. So all these three things, vector, matrix, linear algebra, and eigenvalue, of course, they are the heart of linear algebra. The upshot is that we cannot change the cruelty of cancer, but we can refine the tools that fight it with equations as precise as scalpels. So why this series matters? The cancer is a complex dynamical system where cells interact, compete, and evolve. To predict treatment outcomes, we need more than biological intuition. We need quantitative tools that capture these interactions precisely. So, what is our approach? So, this series will reveal how linear algebra provides the fundamental language to all these three things: how metastasis, the tumor states, as you can represent the tumor states as vectors, and you can predict the long-term behavior through eigenvalue dynamics, and of course drug interactions or cell interactions by matrix operations. By the end, we hope that you will be able to translate biological hypotheses into mathematical models, analyze clinical scenarios using matrix algebra, and interpret published oncology models critically. The same mathematics that describes springs and planets also governs how tumors grow and respond to therapy. So why linear algebra? In cancer. But how do you predict tomorrow's tumor state? Linear algebra provides the language. It's the language to model these interactions systematically. Okay. Today we will learn how vectors represent tumor states and matrices encode the rules of cell behavior. Okay, let us begin with the definition of vector spaces. So vector space over R is the set of real numbers, is a set V with V under addition is a group, and you have scalar multiplication. Which satisfies one dot V equal to V and alpha beta V is alpha beta V, where alpha beta are real numbers. Okay. So biologically, if we want biological model, so there so in tumor modeling, you can take V T. So this is a matrix TID, or you can think of as tuples. So here T, I, D, they are non-negative real numbers. Okay. So what is this T? Is tumor cell count. Which you can take as cells per mm cube. I is immune cell count. So how many good cells are there? And D is drug interaction concentration. So this is drugs for chemotherapy. Okay. So one remark is that, so which is important, that this V above is not a vector space. Why? Think about it. So this is because, this does not satisfy, it is not closed under scalar multiplication, and also it is not a group under addition, because it does not have the additive inverse. So we use R3 3D plane for calculations. But restrict to non-negative reals for interpretation. So R3 is a vector space. Now why this matters? This vector addition models combination therapies. So you can add one chemotherapy and immunotherapy, you can add those combinations, while scalar multiplication models dose adjustments. Okay, so how much dose you need this that can be represented via scalar multiplication. The next part is the matrix algebra. Okay. So linear transformation. So this is a map. The linear transformation is a map T between two vector spaces V and W. Vector spaces is linear if T U plus V T U plus TV, and this is closed under scalar multiplication. The C belongs to R. v u, their elements of v. Okay. This is closed under addition and closed under scalar multiplication. In that case, we will say that T is a linear transformation. So there is a result which is not very hard, but I will keep this. So for any linear map T from Rn to Rm, there exists a unique matrix AT such that T of V is AT of V. Okay. She's not very hard. So if you know what the basis of a vector space, so it's just AT is just the basis change matrix. Okay. So tumor immune interaction matrix. The discrete time dynamics is Vt plus 1 is A. So A is this matrix corresponding to linear transformation, which is, you can think of is at A11, A12, A21, A22. It's a 2x2 matrix with the tumor cells and the immune cells at time t. So think of A as a rule book for cell interactions. So suppose A11 is 1 times 1.1, so it means that cancer grows 10% daily if unchecked. And suppose 812 is 0.3, so that means each immune cell kills 0.3 cancer cells per day. You can have a table on, so yeah, with all these parameters A11, what does this mean? What their biological meaning? And range. So A11, so this means tumor proliferation rate. So range is 1.0.5 per day. A12 is immune killing efficiency. Minus 0.5 to 0. So yeah, it is minus 0.3. 81 is tumor immunogenicity, okay, which is 0 to 0.3 per day. And then A22 is immune resistance. Zero 0.8 to 1.2 per day. Okay. Yeah, sorry. So this one A11 is tumor proliferation rate. Okay. Okay. Next is, now we'll consider the dynamical analysis. So we'll come back to this part later in more depth, but for now I'll just give a brief overview of what does this mean. So this is eigenvalue characterization. So every matrix has some eigenvalues. Okay. So this, which is basically the determinant of which A, suppose A is a matrix, lambda is some number, maybe real or complex. I is identity matrix, A minus lambda I, that's matrix. And for that A is n cross n matrix and I also n cross n. We need a square matrix. Okay. Determinant of A minus lambda I is 0, which will imply, so if you calculate determinant, it will come as lambda square minus trace of A into lambda plus determinant of A is 0. So as an example, so for A, suppose A is in most of the cases n is equal to 2. Okay, you can think of this. Yeah, so here in these two, that is why you have this equation. Lambda square minus trace A times lambda plus determinant of A. Otherwise, you'll get some long difference. So this 2 means 2 in lambda square means n is 2. Okay. So suppose 1.1 minus 0.3, 0.1, and 0.9. So this we have already described what these numbers means, these parameters, and what the biological meaning, what their range is. Okay, in this case, the eigenvalues are, so this lambda is an eigenvalue. Okay, check this. The eigenvalues in this case, their lambda is 2.0 plus minus 2 square means 4 minus 4 times 1.02 by 2, which is basically 1.0 plus minus 0.1414, and I, this is a complex number. Okay, so since this norm, I mean, this is obviously greater than, which is equivalently 0.01, which is greater than 1, the system exhibits slow growth. Okay. So what does this mean? Let me just, so I mean, this actually explains why some tumors persist despite treatment. The system is just unstable. Okay, so what this stability theorem, what this means, so here this is stability theorem, which I will skip again. So this is for any linear system V A Vt, if all lambda is our eigenvalues, they are less than 1, the system is stable. What does this mean? Means tumor shrinks. If all eigenvalues are less than 1, if all lambda I greater than 1, the system is unstable. Tumor grows. Okay, so this is the upshot of this today. So there are some questions that one can think of. So that, I mean, yeah, so maybe we'll do this next time. Yeah, that's it for today, and I hope that you will learn something out of this lecture series. And I mean, the main thing is I am learning. I will try to explain as much as I could. I will share whatever I am learning. Okay.